For my calculus demonstration project, I will be proving that the best angle for an object in trajectory motion is 45 degrees to produce the optimal distance traveled. And I will accomplish this by using not only optimization, but also parametric equations. Now, using parametric equations, it's easy to put the x function and the y function in terms of t. However, it's a little bit more challenging to put it in terms of theta, which is the thing that we want to use to optimize. That's our variable to which we are optimizing with respect to. So first we're going to start off with the parametric equations for trajectory motion. And this is provided in AP Physics, but they could also be derived using calculus. They are 1/2 at squared plus v initial sine theta times t plus y initial. And the x component would be v initial times cosine theta times t. Now, the theta refers to the theta of the angle of the trajectory, and these are the two components that are the parametric equations that I was referring to earlier. So my method for optimizing the angle of the trajectory to find out how far it could go at its maximum is that I split it up into two halves of this parabolic trajectory. Now, as you can see, in a parabolic trajectory motion, it's always symmetrical. That means we could split it up into two halves, where in this half, it will travel the same distance in the x direction as it will travel in this half. Using this information, we could use the theta here in the x direction to optimize how far it would go in the first half. And if we optimize that, we could also double that to estimate or figure out how long it would travel throughout the entire trajectory by multiplying it by 2. This is reasonable because for certain the object of trajectory will pass a point where it reaches a maximum. So if we could use these two equations to find out where that maximum is, we could eliminate one of the variables so that we only have two variables to work with instead of three. So what we're going to do is we're going to try to eliminate the y variable so that we're left with just the x component variable and the theta variable, so that we could use theta to optimize the x function with respect to only one variable instead of with the y, x, and the theta. Firstly, I'm going to solve for t using the x equation. So if we divide all of this to this side, and all of this, these are just constants because in the end, these are just numbers. The initial velocity is just a number. So that's just basically a giant constant. So we can move it over to this side to solve for t. And you get that t equals x over v initial, which is the initial velocity at which the object begins traveling, and multiplied by cosine of the angle at which it leaves the beginning. So that's how we solve for t. And from here, we could move the t into this equation. We basically substitute t for this equation to eliminate one of the variables. Now, if we were to plug in t for the y component equation, we would get this. Now, as you can see, I ran out of space, but all I did was plug in the t for each of the t's in the y component equation. And simplifying this, we would get, there it is. That's what it looks like when it's simplified, and this will make our math a lot easier since there's less of this shit. Now that we have the y equation, we could differentiate this to find out where the maximum is at a certain x value. And that x value is going to be half the distance of the entire distance in the x direction traveled by the object. So to find the maximum, we're going to differentiate y in terms of x. So you would get y equals, and that's what you would get if you differentiated y with respect to x. This is just basic power rule, and this is power rule as well. It might look weird going from x tangent theta to that, but just remember that tangent theta is just a constant, and like the derivative of cx would just be c. So that's what happened right there. Given the y prime equation, I will now set it to 0 to find my critical point where x hits the maximum, or the x value where the y component hits the maximum. So setting this equal to 0, we would get 0 equals. Now that's the equation at any given theta, or any given velocity at the initial point, where the x component, or the x position, would produce the maximum y value. So this is our new equation with just x and theta. Now I'm going to simplify this equation so it looks more clean. I subtract the tangent theta to the other side, so it's negative over there. So from here, all I did was multiply both sides by the v initial squared times the cosine squared, so it looks like that. And ax is over here. And given that a is equal to negative 9.8 meters per second squared, we could plug it into the a in this area, so we would get negative v theta squared and since they're both negative on each side, we could just simply make both sides positive. And using one of the trig identities for tangent, which is sine over cosine, we're able to simplify this side even further. Forgot the x right there. So one of the cosines cancel out, so it would be v initial squared times sine theta times cosine theta is equal to 9.8 x. Like so. Now I'm going to divide the 9.8 to this side so that x is all alone. I switched the order of the trig identities, but it doesn't matter. So finally, I produced the equation for the x midpoint value, which is this point right here, where it produces the maximum y component, or maximum y value. So this is true for every single theta value and every single initial velocity value at which the object begins traveling at this point. So given this equation of only two variables, we can now optimize it by differentiating x with respect to theta. Now since the velocity squared over 9.8 is just some constant, I'm just going to assign it c. So it's going to make our math a little bit more simple. So it would be c times sine theta times cosine theta is equal to x. Now using one of the trig identities, we're going to set this equal to, in the form of sine of 2x. So this side would become c over 2 times sine 2 theta, and that would be equal to x. Now this is much easier to differentiate than that, because we would have to use the product rule. But this is much easier to differentiate. We would just have to use the chain rule. Alright, so if we differentiate both sides, we would get x prime equals c times cosine. Okay, that looks confusing. Two c's. So it's going to look like c times cosine 2 theta equals x prime. Because the derivative of sine is cosine, and the 2 in the inside would have to come out to this side because of the chain rule. So this is our x prime with respect to now, setting theta. This equal to 0, we would get so once again we're applying optimization one more time to find the theta value at which x is at the maximum, because we want x to be at the maximum so that if this is maximized, then this distance will also be maximized. So the entire length that the distance or the object traveled would be maximized. That's why we're doing this second optimization problem. Dividing both sides by c, we would get cosine of 2 theta is equal to 0. And since we are only looking at the angles 0 to pi over 2, or 90 degrees, we're just going to stick with that range. So the only answer within that range of 0 to pi over 2 that fits for this equation would be pi over 4. So theta is equal to pi over 4, or 45 degrees. So that is why most scientists and physicists would say that to produce the farthest distance at a trajectory, you would use 45 degrees. Given this proof, right now I'm going to grab a Nerf gun and a dart and go outside and shoot it at different trajectories to demonstrate how each trajectory produces different lengths that the dart traveled. And it'll probably show that at 45 degrees angles, at 45 degrees, the dart will travel at its farthest distance. In addition to that, I will also be showing other applications of the 45 degree angle idea. Alright, so here we are at the park, and we're going to test out this 45 degree angle theorem. What we have here is the list of data. We're going to try different angles with increments of 5 degrees each time, and we're going to have 2 trials. So what I have here set up is a Nerf gun with my phone attached to it. It has an app where it shows the degrees at which you're shooting at, and we're going to use this to our advantage and try it out. We're going to set up a peg that designates like the starting position. We're going to use this peg to measure from where it lands, and we're going to use that to measure the distance. So this is 30 degrees. Alright, we're going to mark it where it lands. We're going to do 35 degrees now. Alright, we're going to go to 40 degrees now. Prime angle. Alright, let's measure it.
Damn, that was fire.
50 degrees. If our proof is correct, then this should be a little bit less than the 45 degree angle. Alright, this is 55 degree angles. Alright, last angle is 60 degrees. Alright, so we finished trial 1, but we realized that it's probably really boring to watch this, like watch us shoot multiple times and record it. So we're just gonna do trial 2. We're not gonna film it, so the video won't be like 20 minutes long. So you get the idea though.
Alright, so after spending some time in the park, and we were able to compile data regarding how far the dart traveled at different degrees, and as you can see, at 45 degrees it produced the maximum distance possible. The angle surrounding 45 degrees, we're not able to produce farther distances, but we're close to the 45 degree angle. And as you can see, as it moves further away from 45 degrees, the distance got shorter.
So, one of the applications of the 45 degree angle idea is called the Kip-Up. It's a way to get up from laying down. So what you do is you shoot your legs up at a 45 degree angle, and it'll produce the furthest distance with your legs, and it'll make your body spring up along with your legs. Alright, that's good. Alright, so this is what I'm talking about.